Okay. So basically, we'll break it up into 3 phases, where we'll spend most of the time, I guess, on the 3rd phase. The first 2 is really just questions and answers. I want to first deal with anyone having any issues with the lab portion. It's going to be a little difficult to do that here, but the lab portion, at least getting things organized. So I want to ask you that first, which is the bones, the box of bones. And then the next thing I want to do is just deal with old lecture material. If anyone has any questions about the dermatology PowerPoint presentation and the skeletal system, where the skeleton is praying, right? That's the lecture material. Both of that is going to be part of the lecture exam number 2 that's happening this Monday. And then the 3rd section is I'm going to give you spend some time talking about what I consider, or what actually students consider in the past semesters I've taught, the thorniest or the most challenging of the muscular system, which we're all should be beginning this weekend today, with namely something called the action potential. I did it with the other class. It seemed to work out well. And then answer some other questions. So that's how we'll do this. That should take up to 3 hours to do or so. We'll be done by 11 or 10:50. And or is it, we have class until 11:40? 10:50? 10:50, okay. I get mixed up with the 2. The other one is 11:40, this one's 10:50. Yep, we'll do that. So I don't know if everyone's familiar with doing the raising your hand. I guess that'll be easier. I won't be looking really much at the chat box. Just raise your hand. The way we do raise your hand, if you go to participants, no, let me change it. Oh, I'm the host. That's probably why. If you go to participants down on the bottom of Zoom, you'll see participants. There's 12 participants there. If you click on that, there should be another box that pops up, and there should be an option to raise hand. Is that correct? I don't see it at my end because I'm the host.
It's under reactions.
Oh, is it on reactions?
Mm-hmm.
Oh, okay. Okay. I think it used to be over, because I remember it was on the chat box. Okay. Thanks. Was that Eric or Joshua? Anyway, oh, Joshua, thank you. Okay. So, yeah, so you're going to go to reactions, and then you'll see raise hand. And that's probably the easiest way. And then you can unmute yourself and then ask the question. And you could do that pretty much throughout the whole session that we're going to have today. All right, I'll just look at that. So we'll start off with that. So does anybody have, I don't have a box of bones over here, but I could show you some things maybe on the videos or something to give you some relief with some struggles that you're having with the box of bones. So we'll start off with that. Does anybody have any questions on the box of bones or the laboratory section? Yeah, Margaret.
Just on, so the skull that we have, the box of bones, it's not a very good model. So for the sphenoid bone, the greater and lesser wings, you don't have that with you, right?
No, it's a pretty good model. You don't need to print it up or anything. Okay,
I don't know. I can figure it out. It just doesn't look like all the pictures that are on the PowerPoint and other pictures I've looked up. It just, I don't know. I don't find it extremely, I don't know, I found it difficult to determine. Anyways, never mind. Don't
Okay.
worry about it.
No. But what is it that? Yeah. What is it though that you're having issues with though? I'll try and.
Well, I just find it hard to find the differentiation, the lines, the fusion lines between the sphenoid bone and whatever's in that part of the frontal bone. It's just, I don't know, it doesn't look like all the good pictures online, right? Because the pictures are going to be better. It was just a little harder to figure out. That's all.
On the pictures, they're showing like different colors because they're showing you where it is. But in real life, you're not going to really see all these sutures. I mean, you'll see them faintly; they're there. But the structures you should be able to see, like the lesser wing and the greater wing. You should be able to see those. You should see, let's say, on the ethmoid bone, you should see the where the cribriform plate is, where there's little holes in there.
Yeah, I can find that. I can find it. I found it. I guess so that's really all we need to know is the lesser wings and the
right. Exactly. And if I put, let's say, a sticker, like if I put a sticker on the lesser wing, I'll ask, like, what is this bony structure and the bone that it belongs to?
Okay.
You know, you'll get I'll show you better with these things on Monday after class.
Okay.
Or not after class, but after the exam. And I'll give you other examples of possible questions. I'm going to use the same bones, some other bones too, but it's pretty much you'll be able to see it.
Okay.
Yeah, you'll see it. It's maybe easier to do it that way.
Okay.
Yeah.
And then just one other question, and then I don't have any more.
No
So
problem.
in your PowerPoint, right? I've learned to pay attention to when you say the word accept, right? So you talked about the sweat glands, the American and the African, and you said at one point it's found everywhere except parts of the external genitalia, right? For the American.
Mm-hmm.
But then in the next portion of the slide, it talks about the African glands, which are found in, it says external genitalia. So the found, and then the next gland it's found, it is found. I found that confusing.
All right. Hold on, I'm going to open up the PowerPoint so I can see exactly.
Okay.
Because it could be a typo. Hold on.
I think what I got out of it is one gland it's not in, and the other gland it is in. So in American, it's not going to be in the genitalia at all, but it is going to be found in the African.
Right. But I'm going to make sure that that's what it's saying. Hold on, I'm going to share the screen. Where is it? Share screen. Okay. Just trying to get all these boxes away. Okay. So this is where you're seeing it, right?
Yeah, I think it's slide 43.
It's 30. So here I'm saying the American is in certain sweat glands. I'm not saying which ones, but then when I start talking about this one, that's 43.
No, on the slide itself, it specifically says parts of the external genitalia. And
With this slide?
no, not that slide. It actually, you have it written on the slide. So maybe it's a little right here, right there, that one. So here you're saying sweat glands, not in the lips, nipples, parts of the external genitalia. And then you go down another slide or two. And right there, apocrine sweat gland located in the external genitalia. Go one more slide down.
Right here?
Yep.
Right. So what I'm saying is here, parts of the external genitalia.
Yeah.
Not
So
all, but there
Right,
is some parts. So the other parts that are here.
right, but I find that confusing. So parts of, but you're
Right.
not saying what parts. And then the next line, it's located in the external genitalia.
Right.
So what parts?
So it's going to be in the pubic area. For
Okay.
instance, okay, yeah. So all right. So I don't want to go into it because we didn't do the reproductive system. So in women, it's on the external labia, but not the internal labia.
Okay.
But we didn't go over that. You know what I'm saying? Because that's A&P too. So
Yeah,
I don't want to confuse you even more and have
Okay.
you know those parts when we were not even doing those. So
Okay.
when you get to there, you'll learn more about the apocrine glands and you'll know what parts those are.
Okay. So I don't need to worry about that.
Right. I won't ask you. I can't give you reproductive parts if we didn't do them. Absolutely.
Okay.
Right. Yeah.
All right.
I can see where that gets confusing, but I kind of cut down the confusion because we didn't do the anatomy of reproduction.
Okay. Great. Thank you.
Does that make sense though?
Yep. I just
Okay.
wanted to double check. Thank you.
Yeah. But yes, just to be complete, it's on the external, for women, it's on the external labia, but not the internal labia.
Okay. Thank
Okay.
you.
Yeah.
That's it. No more questions.
Yeah,
for
no
me.
problem. No problem. All right. Anybody else have questions about at least the lab section, or we could go right into lecture section? And anybody have any questions on, let's say, dermatology?
Really?
No. How about the skeletal system in terms of where the skeleton's praying, the lecture material? The session's going to go faster than expected. No? So we're good for the exam on Monday then. Yeah.
I mean, my only question for the exam on Monday is the osteogenesis part, ossification.
Yeah.
There's a lot of steps, right? I understand it. I've gone over it about 100 times. Are we going to need to like list the steps?
You won't have to list the steps. No, you may have to put them in order, but they're there. They're already written. It's almost like multiple choice.
Okay.
So the steps will be there. You would have to put, let's say, of the multiple choice, is it 2,
1, 2,
4, 1, 2, 3? You know what I'm saying? Or is it?
Okay.
You know, but the steps will be there. The steps will be there.
I'm just trying to figure out a way to, remember them.
Just keep on watching the video on ossification on the two.
Okay.
The two ossifications, but you also have the appositional, which is more of the how osteoclasts and osteoblasts work together. That teacher was explaining with Bob the Builder and Claude the Harvard. That seems to be much more easier to manage than the two ossifications. Yeah, I would imagine the ossifications or osteogenesis is probably the toughest part of the whole PowerPoint. Yeah. And it is. I mean, it's physiology. And like I have said on day one, students have more issues with physiology than anatomy. Anatomy is just memorization, whereas physiology is conceptual.
Right.
Yeah.
Yeah. I understand it. I'm just trying to come up with a way to remember each step. So, okay.
Yeah, just keep on doing it. There's probably some more videos. Now that you understand it, and then you just put the steps in order, you could probably go onto YouTube and just type in endochondral ossification tutorial or lecture or something like that. It's going to be the same exact thing, since you already have it absorbed in your brain, but you just want to see it differently. Another teacher or another video or animation will be done, and it's the same thing. It's just that you're seeing it at a different angle.
Okay.
And I think that will reinforce it. That's what I kind of learned to do in medical school was, all right, I understand this concept, but let me look at another book, because it's the same thing, but let me see how another author is going over it. And I would do that, let's say, for 2 or 3 books. And it just reinforced it in myself, like, oh, okay. And also with that is you always get, like, I guess when I talk to other professor colleagues, what's one thing that students always complain about? And it's like, well, we studied this material, but I don't like how the teacher worded it on the test. And it's not anything bad about wording it differently. It's about students memorize, like what you may be doing, or a lot of students is memorizing word by word what each one of those steps are. And then I put it up, on the exam, and it's not word for word. It's using other words, but it's the same concept. So it's not, so if you look at other way of people seeing things, because if I asked everyone here, if there's like 12 people in here, and I say, like how oppositional growth happens, I bet you everyone will do it differently, but it's the same thing. It's like, yes, or mitosis, right? If you went, and that's an easier one to use. So mitosis only works one way. But if you have, let's say, 10 teachers or 10 students explaining it, it's the same thing. They're just using different words. So if you see more of that, it'll reinforce it in your brain, to say, hey, look, this is the same thing. Why am I making this more complicated? And it's not. You just need to see how it's done in different things. So yeah, I encourage students to, once you understand a pretty hard concept, to go and look in the book, or to see how they word it, or look in like I said, a YouTube video or something like that.
Okay.
And do more of that. Yeah, that'll reinforce it. You're not wasting time, is what some students say. Well, I already understand this concept. Let me go to the next thing. It's a good reinforcement thing to see that maybe there was something that I just breezed right through, and then the other one they spend more time on. And it's like, oh, now I understand what's going on. The way they fits like a lock and key. Now I understand it.
Okay.
Yeah.
All right. Thank you.
Yeah, no problem. No problem. What other questions do people have about the lecture, lecture material? So dermatology or skeletal system with the skeleton praying. No? Okay. So what I'm going to do then is, I guess we'll get started with the muscular system. Now, this material that I'm going to do is not going to be on Monday's exam. Okay. But I think I had 1 or 2 students, they don't want to start something new, or they inferred that they don't want to start something new until the exam starts. Well, we have to get started with this because we're in an accelerated course. Otherwise, you're going to need, I know students will need to spend more time. Can everybody hear me? Something came up on my screen that said my internet was unstable, but I don't know. So since we're in an accelerated course, I know that students need to spend more time on the muscular system, because there's more concepts, as we just talked about with the skeletal system and osteogenesis or ossification. That's a conceptual thing. There's a couple of big conceptual things happening in the muscular system. One is the action potential, which I'm going to do for you today. The other thing is the actual contraction of the what actually makes the muscle contract. And you've seen all those striations. You're going to learn now in when you do the PowerPoint what those striations. Why do they have those striations? It's the way the myofilaments, or specifically the actin and myosin of muscle, is organized, and they move too. They're going to do this kind of motion. So these are big concepts, let alone there's also a neuromuscular junction, which I'll talk briefly about today. So I know you're going to need a lot more time with this one, and that's why I want you to start a little bit earlier before the exam begins. And then the next one is going to be, we're going to go right into the nervous system, and it's called Intro to the Nervous System. It has a scarecrow on the front. There is going to be some concepts that are going to be built on from the action potential, which I'm going to do with you today. But there's other things too. There's a lot more anatomy in there also. So and those two PowerPoints are what's going to be on lecture exam number 3. So because there's a lot more concepts in there, you need to start this a little bit earlier. And I guess just be able to know how to juggle with this. So I just want to get you started with the muscular system, at least the action potential. And, I'll do a little bit more after the exam on Monday. So anyone have any questions about why I'm starting a little bit early with this? No? Okay. All right, so I'm going to share my screen and just introduce you to this. So this is going to be our next PowerPoint. Now, like we did the bones, the way I broke up muscular system, there's 2. There's a lecture portion. I'll call this obviously Arnold Schwarzenegger. I'll be back, and 40 years later, oh, my back. There's a difference. And then there's also going to be a lab portion, which we're not going to start until later on, probably sometime in July, where we got models of muscles and stuff. So it's the lecture portion that we're going to do over here. And the first part or so is going to be more general stuff. Also, if you could see this, I just want to show you how I organize my PowerPoint since I have it set up this way. Basically, if you see a red block over here, those are like the big subjects. Like this one's called muscle types, and I go into this. This is connective tissue and skeletal muscle. Then I have sometimes a green one. That's like, this is a subject right here, and this is a sub-subject, if you could have that, like a subtype, like underneath there. These are good points, like if you want to go grab a sandwich, or if you want to, these are good places to have a stopping point, okay, before we go into a big concept. So the red blocks and the green blocks. The red blocks are big, they're big topics, but then I kind of split them up into green blocks for even smaller ones. So here it is over here, and so forth. So, and purple here is just more about diseases and how to apply the material. But again, it's also a good stopping point also. Okay, and then we go back into reds and so forth. Okay, abnormal findings, like I said, diseases, more like purple. So at least you have an idea of how I'm organizing this. This is pretty much straightforward stuff. Muscle types is just going to be review of histology, whether you want to do that or not. It's a part of muscle, so I got to put that in there. What I'm going to do for you is basically starting with 59. I know I'm jumping there, but I'd rather do the thorny or the most challenging stuff. And what it is I'm going to start off with like 59. Now, I'm not going to use the PowerPoint. I'm just going to use my drawing tablet, and everything that I'm going to do on the drawing tablet, you have on video. Okay. but I'm basically going to do this whole section on the action potential. And we're going to go back to some review stuff from what you should have learned from Bio 121. And then we're going to apply it to something that's over here. Okay. And that's pretty much it. And then there's the other thing that's going to be a little challenging is the skeletal muscle contraction. But I have a lot of animated videos that I found on YouTube that is going to really help you with this. And I embedded them in my own video lecture. Okay. But that's another big concept. And then the other one is the neuromuscular junction, which I'll go with you also too, briefly here. Okay. So, so any questions about how I'm just going to do what I'm going to do for you to for the rest of the time? Okay. Now you could do two different things with this. I'm gonna, like I said, I'm doing the same thing on video, except I'm using the drawing tablet. I would normally do it on the whiteboard and do my art therapy up there. But you will have everything, so you could just either sit back, eat your popcorn or whatever, and just watch me, and then you could also and that'll allow you to absorb it, or you could take notes and you could draw things with me also. But it might be better just to watch everything. I'll have this recorded, and you could I'll post it and send it all to you. But whether you want to watch this again or not, everything is on the video lecture. Okay, so let me switch over to the whiteboard. Share screen, whiteboard. Okay. Erase this. Okay. And if you have any questions, again, just raise your hand. One second. Where's the whiteboard on here? That's not the whiteboard. Hold on. Let's see. Whiteboard. Sure. Okay. Sorry, I'm just getting everything organized. I got these windows open. It's got to stay there. Okay, that's why. Okay. All right, so let me explain to you what's going on over here. What a neuromuscular junction is. Again, you're going to have. Oh, let me erase it. Draw. Okay. My drawings might be a little bit sloppy because I'm drawing with a tablet, not freehand, so to say. All right, we all remember our dendrite neuron, so to say. And then you got the axon. Now, what we did is that, just for review, we have our cell body over here with the nucleus. You got your dendrites over here, and then the axon. And then you have the axon terminal, the end of the axon. Now, that could be attached, or that could get either very, very close to another neuron, and then this is going to tell another neuron what to do, or it can also, or not also, it's either going to attach to another neuron, or it'll attach to, let's say, a muscle. Okay. And Just use another color. Blue. So this area here is called a neuromuscular junction. It's where the neuron touches the muscle over here, so the neuromuscular. Now, the idea over here is that it gets very, very, very close, but it never touches the muscle, okay? When we look at it closer, we're gonna see an area that kind of looks like this. Hold on, let me just do it in the same colors so you can get an idea. Do black, so this, oh, come on. Okay, so what happens over here? Okay, so this what I circled here is a close shot over here. So you could see this is we call this the neuromuscular junction. Okay, this is a synaptic cleft that's in here. And this is the presynaptic membrane. This is the postsynaptic membrane. Again, you're going to get all this on the in the video also. It gets very, very close, but never touches. Now, there's a lot of things happening over here. So what happens here, just so you get a view of this, use green. There's going to be this is going to tell the muscle what to do. How does it do that? Is, remember, there's going to be an action potential that comes down here, down the axon. And when it comes down to the axon terminal, so it continues down here, things are going to happen over here. And I don't want to go into that today. I'll talk to you about it if you have any questions about it after the exam on Monday. But things will happen, and there'll be things getting released over here. These are called, the items that get released are called neurotransmitters. And this is going to send another action potential on this side over here onto the muscle. And within the muscle, the action potential will then go down into the muscle like this and cause a contraction. Okay? There's certain things that will be able to make the neurotransmitter, these little dots, to make them go from one place, from this end here to this end here, until it reaches its receptor. And that's what really starts this action potential. But then I go over diseases, things like botulism and the black widow spider, that either they're going to block this receptor, and then you're not going to have a neurotransmitter hit here, which means you're not going to have a contraction, or there might be too much of the neurotransmitters coming out, and these receptors are going to get flooded with all those neurotransmitters, and the action potential is going to go so fast down here that you're going to have a sustained contraction. So I don't want to jump the gun over there, but understanding what this is, you're going to learn about other diseases that to reinforce what's going on. So it reinforces, okay, that's what the neurotransmitter does. That's what the receptor does. If we don't have the receptor, what happens? If we have too much of the neurotransmitter, what happens? If we have too little of the neurotransmitter, what happens? So this area here, the neuromuscular junction, is another big concept. They usually, students usually can handle this one much better than the action potential. So I just wanted to give you an overview of what this neuromuscular junction is today, but I now want to just spend a lot more time talking about the action potential itself. This green line, what is this all about going down here? And then later on, we can then apply it to what it does to the muscle itself. But what I want to do today is talk about what this is, this so-called action potential, which is a big concept, okay? All right. Does anybody have any questions at this point? At least you have an overview of where this action potential is and why the action potential is so important. Because if we block this action potential over here, you're not going to have this neurotransmitter go over here. It means that you're not going to have a contraction. If it goes to another neuron or it goes to your brain, then that message is that action potential is not going to go up to your brain to have your brain figure out what's happening. For instance, if I stick a needle in my hand, then there's going to be an action potential that's going to go from my hand into the neuron in my arm, into my spinal cord, up to my brain. But if I put something on my hand that will stop the action potential, then technically that action potential won't go to my brain and I won't feel pain. So you can see where this is all going when we deal with pharmaceuticals and you got pain relievers and stuff. So action potentials are a key to this thing, and you'll be needing to use it in so many different ways. But I need to break down what an action potential actually is. And we're going to talk about ions and things. So does anybody have any questions at this point on what I'm going to be talking about or what I have talked about? Just raise your hand. No? Okay. Wait, did I see someone raise their hand? Lynette? Okay, you can unmute yourself.
I just wanted to know, like, when we have, like, if we have surgery and we have, like, lidocaine and stuff like that, is that kind of how that works? Like, they kind of prevent?
Yes, there's going to be, well, general anesthesia, what it's going to do is not that it's going to block it from, let's say you're having surgery on your stomach. That works a little bit different because it actually goes right to the central nervous system. It's going to block things in your brain. But if you have lidocaine, let's say you're awake, yes, the lidocaine, you put it on your hand where, let's say they're going to do some kind of, you cut your hand and they want to do some suturing, like sewing. Yeah, they're going to put some lidocaine there and they're going to, so you're awake, you're not feeling anything. It's all numb. And that's where that comes in. But yes, in a way, it's going to be doing it in the brain for general anesthesia, but it's not going to be in the area where they're actually going to do the surgery. It works a little bit different over there. But yes, we're talking about action potentials.
Thank you.
Yeah, no problem. Anyone else? And we won't go through what general anesthesia is versus a local anesthetic. That's way over the scope of this course, but at least you understand what the action potentials are, so that when you get into nursing or whenever you need to take, let's say, pharmacology in another course, you have the idea what an action potential is, and then wherever they're going to take you with that information, you have the baseline of what it is. We good? Okay, so I'm going to okay, so I'm going to erase this. So now you have the idea of what a neuromuscular junction is. These are clear. Okay. So now what we got to talk about is the action potential. Okay. Now this is where I'm going to get you guys interactive with here. All right. So again, if when you raise your hand, go to, as Joshua reminded me, go to do you see it down there still?
Yes, the reactions.
Yeah, I don't get reactions on my end. Okay, that's why. Okay, so if you look down the bottom, you'll see reactions down there, and just raise your hand. All right. So here's my question. when we deal with cations and, well, we're going to go really back further. What's a cation and what's an anion? Who can answer that? What's a cation? Yeah, I can't see people's raising their hands unless they click on that, because I only see like 4 people at a time. So it's easier if you just click on that. Okay, yeah, there I see. So Margaret, yeah.
A cation ion is a positively charged ion.
Okay, and an anion?
It's a negatively charged ion.
Okay. Good. So everybody understands cation. Think of a happy cat, like a positive cat is a positive ion. Anion is negative. So here's my question. What's that? Oh, someone says that. Okay, so here's my question. What is the most abundant cation outside of a cell? Anyone? Eric?
Potassium.
No, outside a cell.
Oh,
Potassium is the most abundant cation, which would be my next question, inside the cell.
got it.
Well, what's the most abundant cation outside of a cell?
Sodium.
Sodium. Okay. What's the most abundant cation or anion outside the cell? Anyone? Eric, do you know?
Magnesium.
No. Magnesium is actually positive.
Oh, calcium.
That's positive too. Anyone? It's chloride. Okay. So let me draw something for you now. All right. So we have, I don't want that color. Sorry, I'm just getting colors here. All right. So we have a cell. Okay. And the best way to understand this is there's something I created or came up with called it's called a salty banana. And this will help you to memorize what this is. So, okay, so salty banana. Let's see if I can draw this. Okay, a little cross-eyed. And here. Okay, so now I don't have, I guess just unmute yourself to answer this question. In a banana, what's the ion that, what is a banana loaded with? What kind of ion? Anyone?
Potassium.
Potassium. Okay, well, that's something we learn, much younger in age, right? So inside a banana, it's loaded with potassium, and that's the abbreviation for potassium is K. Okay. And then what do we know as table salt? What's the formula for table salt? What is it made out of?
Sodium and chloride.
Right, sodium chloride. So we get here, we have sodium that's going to be out here. Right, and then we also have chloride, which is Cl, right, with a negative. So this is my little mnemonic to help you with this. If you know the salty banana, Outside the cell, it's loaded with sodium and chloride. Inside the cell, it's loaded with potassium. Now, here's a little tough one, but what is the most common anion found inside of a cell? It's a little tricky. It's actually phosphate, which kind of looks like this. Sorry. Okay. Now, I'm not going to ask you too much about phosphate, but I have no mnemonic for the phosphate, but I think I've given you at least 90% of the memorization is cut short now because you understand what this whole thing is about the salty banana. Okay. This is the same concept of what a cell is. Okay. So what I'm saying here, and I'm going to just use these colors because it's going to be much easier for me to deal with this, is that outside the cell, and I'm going to use sodium as red, outside the cell, it's loaded with chloride. I'm sorry, sodium. Now, with that said, that does not mean that there isn't any sodium inside. There is, but it's just not as much as there is outside. Okay. Likewise, we have potassium, and it's loaded inside with potassium. But again, that does not mean that there is no potassium outside the cell. There is, it's just not as much. Okay. Now I'm going to hold off with the chloride, but you would have chloride on the outside also. Okay. Any questions about where's potassium mostly located and sodium? This is old stuff that you should learn from Bio 121. Now, the other thing I want to do from Bio 121 is tell you, okay, if we have, and let me erase this for a moment. You don't need this. We'll do this. Okay. Just so it's a little bit easier to see. So if we have more sodium outside the cell, than we do inside the cell, if we have a sodium channel here, a channel, a gate, a doorway, that this allows sodium to go into the cell or out of the cell. Which way would you expect it to go? If we have more sodium outside the cell than inside the cell, does the sodium, and again, don't raise your hand, just unmute yourself. Does sodium want to go into the cell or does it want to go out of the cell naturally?
Into the cell.
Into the cell. Why does it want to go into the cell? What is that concept?
It has a high concentration to low concentration.
Right, and what is that called? What transport mechanism is that?
Simple diffusion.
ATPase.
That's simple diffusion.
Oh.
Because if I was in a classroom with you, if we have, let's say, 100 people out in the hallway of the classroom, and in the classroom we only have 3 people, if that door opens, we expect everyone to go inside the room. we're going to go from a high concentration to a low concentration. And that is just simple diffusion.
Diffusion.
Okay. Likewise, I'm going to erase this for a second. If I have potassium and there's more inside the cell than we have outside the cell, and we have potassium channels that will allow things, potassium to go outside or inside, which way does it want to go?
Outside.
It wants to go outside. Why? Simple diffusion. It's going to go from a high concentration to a low concentration until it reaches 50-50, right? Until it reaches equilibrium. We learn that as isotonic. Okay? Does everybody understand that? Yeah, no questions? Okay, now let's do the next step. If potassium goes out of the cell, these gates open, and potassium goes outside the cell, does inside the cell become more negative or more positive?
Negative, it depolarized.
Right. Let's not use the word yet, depolarizing. You're jumping the gun, but yes, you're absolutely, well, it's actually repolarized, but we'll talk about that in a moment. So right now, yes, if potassium goes out of the cell, we're losing all this positive charge. That means inside it's going to be more negative. Now, this is a good example. When I was talking when I was talking with Margaret earlier, is that I don't like the way teachers word things. You see, Dr. Gamaro says, you know, that it's going to become it's going to be more negative inside, but the book says it becomes. I'm sorry, that I said it becomes, yeah, it becomes more negative inside. But then the book says, well, it gets less positive. That's this, if you just let it absorb, let it register in your brain, something that becomes more negative is the same thing as saying it becomes less positive. Does that make sense? That's why I'm saying, don't just memorize, you need to understand the concept. That's what makes it a little bit difficult with physiology. They like to use different terms, or not different, well, yeah, different terms, but it's the same thing, okay? So if potassium leaves here, the inside becomes more negative, but it also means that it's going to be less positive, okay? So don't let those little words screw you up. It just means the same thing, okay? All right, that's my dog barking in the background, sorry. Okay, likewise, I'm gonna go back to this, erase. We had more of the sodium out here. Than inside. And then we open up these gates, the sodium channels. And again, I'm using color coded, red being up here, okay? And you told me before that when these sodium channel gates open, that sodium is going to go inside. If sodium goes inside, does that make inside the cell more positive or more negative? Anyone, you could just unmute yourself.
It becomes more positive.
Right, it becomes more positive. Or it becomes less negative. Am I not right in saying that?
Yeah.
Yeah, okay, so don't let those two, the wordings of those, confuse you. It means the same thing. Okay, now this is where, the hard thing here is that we have to deal with something called a graph. And I understand that when teachers start drawing graphs, students start saying, oh no, we don't want to do, they start losing it. Okay. I don't want you to do it. We're going to go step by step and show you what's happening here. Okay. Now, there is on this axis is time. Okay. On this axis is going to be millivolts. Now, I have to also tell you here is that there's something called a resting membrane potential. A resting membrane potential is that we are going to see what this membrane is, what the charge is. The best way I can explain you is that if we put, let's say, a probe inside and a probe outside and hook up this to a meter, so we could see what the charge is over here compared to what over here is. If we had, let's say, positive 50 over here and negative 50 over here, what would be this charge? Anyone? If we have positive 50 over here and negative 50 over here, what would this membrane charge be?
0.
0, okay? But that's not what's happening over here. And if it's 0, then this is equal. There isn't going to be any kind of action potential because it's already reached its goal. The goal is that it wants to reach 0. Once it does, then there isn't anything that's going to, there's nothing going to go in, there's nothing going to go out because it's happy. It's it's isotonic. But that's not what our cells are. We want the potential to always go to 0. So it's always like there's this tickle in your nose that always wants you to have a sneeze, to have a reaction, to have some sort of activity. So to have 0 would mean that you're basically dead. You wouldn't do an action potential, which means you wouldn't do a muscle contraction. You couldn't tell another nerve what to do. So we wanted to have this little tickle in our nose. We want some sort of not 0. So our resting potential in the cells that we're going to talk about is our magic number is going to be negative 70 millivolts. Okay, some cells might have different things, but for muscle cells and nerve cells, our magic number is going to be, the resting potential is going to be negative 70 millivolts. Okay, now there's another thing I have to also tell you about these channels over here that explains a little bit about why it's negative 70. Okay.
Before you say that, so at negative 70, it's sort of just sitting there waiting. That's the ideal spot before it receives stimulus.
Right. That's at rest.
Okay. It's just sitting there waiting. It's waiting.
Correct. It's going to sit there waiting until an action potential changes it.
Okay.
Because we're talking about a resting membrane potential, not an action potential.
Right.
So when you're sleeping, your muscles are all basically at negative 70 millivolts. They're not doing anything. When you're walking, they're going to change.
Okay.
Okay. All right. So let me talk to you about these channels being leaky and what that means and the significance of that. So these channels here are leaky. So in other words, when they're closed, it's still allowing they're still allowing some, not a lot, but some sodium leaking in there. It's like your faucet. You turn it all the way so it's really tight, but you're getting drips. Okay, not a whole lot, but it is coming in. So when that happens, even though these are closed, we're still getting some positive coming in. But we also have the these potassium channels that is also coming out, because these potassium channels are just like this, they're leaky also. So if these are closed and these are closed, some potassium still coming out, very little, but some of it's coming out and some of this is coming in. This here, the potassium channels are more leaky than the sodium channels. And I'm just giving you numbers. It doesn't mean anything, but just so you have an idea, is that maybe, you know, you're having, let's say, one sodium coming in, one sodium coming in, one sodium coming in. This one's allowing like 3 potassium going out, 3 potassium going out, 3 potassium going out. So this is more leaky than this, but they're both leaky. So if the potassium channels are more leaky, is the inside of the cell more negative or more positive if the potassium is leaking more than the sodium? Anyone? Okay, let's go back to this. Let's go back to this concept. If sodium's coming in, does it make inside the cell more positive or more negative?
More positive.
More positive. If potassium is coming out, is inside the cell becoming more negative or more positive?
Negative.
Negative.
Good. Okay. So if the potassium is coming out more than their sodium coming in, is inside the cell becoming more negative or more positive?
Negative.
More negative.
There you go. Okay. So because these are always leaky, both of these, but potassium is more leaky than the sodium, that's contributing why the resting membrane potential is a negative charge. Does that make sense to everyone? Okay. The other contribution of why this is more negative, we have other things in here that have a negative charge, namely proteins. We got a ton of proteins in here that have a negative charge. Because of that, that's also going to contribute why inside this cell is more negative. And that's why when you add up you have these probes, this and this, why it's not 0 is because of, one, the potassium channels are more leaky than the sodium channels. And we have a lot of other negative charged things in here, namely certain proteins. And that's why we get this negative 70 millivolts. Does that make sense to everyone? I just want to explain to you why we have the resting membrane potential is negative 70. Any questions at this point?
So inside the cell to begin with is loaded with potassium already, right? Which is positively charged.
Okay,
And then more positive sodium is coming in,
correct.
but then more positive sodium is leaving.
No, not leaving. Positive,
I'm sorry, potassium, more positive potassium is leaving.
correct.
I said it backwards, sorry.
That's
And then
right.
there's already some negative stuff in there,
Yep,
so it becomes less negative,
correct.
or
And
more
that's
negative.
right, more negative. And that's why we have this resting potential as a negative charge. You may or may not learn in future classes that there are other cells that would have a positive charge or a less negative charge. Meaning like negative 70, it might be like negative 50. We're not going to go there. Our magic number that we're going to use is negative 70, because the two cells that we're really going to concentrate on in A and P is the muscle cell and the nervous cell, or a neuron. And those both have a negative 70 millivolts. So instead of making it complicated, I don't want you to think that every cell is negative 70 millivolts, but the two that we're going to talk about is the muscle cell and nerve cell. Okay. Questions? Okay. So let me
Yeah, one question, where's the
ahead.
chloride? Where's the chloride in all
The
this?
chloride is out here, and I'll get
Okay.
back to that. Yeah, because we have more, like the salty banana, there's more chloride. All right, so we'll use that just so you could, but I'm not going to talk about that right now. But let me just show you so you could understand. It's the same concept. What we're going to have, this is getting really busy. So we have more, so chloride will be, let's say, green, and it's negative. So we have more chloride on the outside than we do on the inside. And if we have chloride channels, would we expect the chloride to go into the cell or out of the cell?
Into the cell,
Into the cell. Why? Because of
simple diffusion.
simple diffusion. It's going to go into the cell. Now, just to, it's the same concept, but it's going to be the opposite. If sodium goes into the cell, does that become more negative or more charged or more positive inside the cell?
More negative.
Right, because chloride has a negative charge. It's an anion. So don't think that anything that comes in is going to make it positive. You got to look at the charge of the ion. Sodium, because it has a positive charge, when it goes inside, it's going to make inside more positive. But if chloride goes into the cell, it's got a negative charge, so that's going to make it more negative. So you need to know what the charge is to understand what's going inside the cell, what's happening to inside the cell, the charge inside. See, this is very conceptual. The only thing you have to memorize, really, if you think about it, is the salty banana. Because everything else, simple diffusion, you learned about before, what sodium is and potassium in terms of charge, and maybe understand the concept of leaky channels. But basically, if you understand the salty banana, that's really all you have to memorize. Everything else that we're talking about here is conceptual. That makes it tougher for students to absorb. And that's why I want to spend some time talking about this. Other questions before I go further? Okay. All right. So let me clear this because it's getting a little bit busy. All right. So we're going to have the cell. And I'm going to have my graph over here. Again, this is going to be time. We're going to have millivolts over here. And I'll even use, now that we learned it, we're going to have 70 millivolts here. Again, just so you can understand, sodium will be red. Potassium will be blue. Okay. Okay. So right now we have a resting potential. And I'll make that. I don't know how well that's going to do, but let's say, no, I don't like. Try to pick this. I'm going to try and make this all color coded for you guys. Let's say the resting potential. I use brown. I guess that'll work out. Okay, so we have a resting potential. I'm using brown here. It's going to be -70. Okay. Now, nothing's happening to the cell. It's staying at -70. Nothing stimulated it yet. Okay. Then all of a sudden, something's going to be stimulated, or this cell will be stimulated somehow. Okay, the neuron or the muscle cell is going to be stimulated. It could be pressure. It could be light. It could be a sound. Anything, whatever that cell is, to respond to some sort of stimulus. Then what's going to happen is, I'm going to use this thing here. There's another magic number for you, negative 55. Then what's going to happen is these sodium channels are going to start to open. Now, they're not going to open all the way. Remember, these are already leaky. And sodium, like you told me, is going to want to go into the cell. So what happens here is that the cell gets stimulated, and if sodium goes into the cell, does it want to become more positive or more negative?
Positive.
Positive. So what's going to happen here is that it's going to start going up as sodium's coming in, right? It's going up. Now, here's what's important. If it reaches negative 55, the action potential, it's going to shoot skyrocket up. Why? Because the sodium gates have now opened up very fast. And that's going to allow sodium to pour inside the cell. And what happens is that it actually goes in so much that it passes 0 and it goes to about positive 35. You'll see some books saying positive 30, other books saying positive 40. I'm using positive 35. I'm not, on my exams, it'll be around that range. I'm not going to ask you positive 35 or positive 40. It'll be that range. So what's going to happen is that it reaches positive 35. And this pouring of sodium coming into the cell is going to become positive 35. We call this, and this is where Eric jumped the gun, but we call this depolarization. Depolarization is when it becomes more positive, and it's due to sodium coming into the cell. Okay? Any questions so far? What happens at positive 35 is that these sodium channels, bam, they close very, very fast, so that sodium can't go back in, can't go into the cell. And that's why, it happens at about positive 35. Now what also happens at the same time that the sodium channel gates close, we also have potassium gates over here. And we have more potassium inside the cell. At the same time that the sodium channel gates close, potassium gates open wide, very fast. And that's going to allow the potassium to go out of the cell. If potassium is leaving the cell, does that make inside the cell more positive or more negative?
Negative.
Negative. And what happens here is that it's going to go skyrocket down. We refer to this as repolarization. And repolarization is due to potassium leaving the cell. And that's a good question I might have on the test. Depolarization is when sodium enters a cell, leaves a cell, potassium leaves a cell, or comes out of the cell. So again, depolarization is due to what? Anyone?
Sodium leaving the cell.
No, sodium coming into the cell.
I'm sorry, yeah.
Right?
That's
You
what
see
I
what I'm-
Yeah, that's what I meant.
that's good. That's okay. That's okay. But that's what I'm saying. It could get confusing. All right? Is you got to know where these are all going. Repolarization is due to what? Potassium leaving the cell, potassium coming into the cell, sodium going into the cell, sodium going out of the cell.
Potassium leaving.
Potassium leaving.
Potassium leaving. Okay, that's not memorization. The only, like I said, the only memorization is a salty banana. You know that there is more potassium inside the cell than out of the cell because of the salty banana. The concepts, putting it all together, applying it, it's more conceptual. Okay, now what's going to happen here is that I talked about when it reached -55, the sodium channels are going to open very fast. When it reaches +35, the sodium channel gates close very fast. At the same time that the sodium channels close very fast, the potassium channels are going to open very fast. Now here's the difference. When it gets to about -70, the potassium channels are going to close very slow. Because they close very slow, think of, again, I would do this in the classroom with you. I would have the door open, and if I have, let's say, 3 students leaving the room from that doorway, and I close the door very fast, I can't get more of those students to leave the room because I closed it so fast. But if I close the door slowly, can you imagine 3 students still leaving because they could squeeze out because the door is closing very slowly? Can you see that? If you can see that, then you're actually going to see that there's going to be a few other potassiums, even though these are closing, a few potassium is still going to sneak on out of here. If we have a little bit more potassium sneaking on out of here, does that make the cell inside more negative or more positive?
More negative.
More negative. So what's going to happen here is that this is going to go down even further than -70. It usually goes down to about -85. This area here, where it goes down even further, we refer to that as hyperpolarization. Is that clear for everyone? Yes? No? Does it make sense to everybody? Yes?
Mixed. Yeah.
Okay. Then what happens over here, when it reaches -5, these gates, the potassium gates, are now fully closed. It just closed very slowly, but now they're fully closed. Then what happens now is that the sodium channels and potassium channels, they're back to their leakiness. And it's going to go back to -70 so that this reaches its resting membrane potential. That's the action potential. Now, an action potential that I showed you going down the axon, one action potential is not going to do any work. It's like you taking a electric wire that's hooked up to a lamp, you plug it into the outlet, and if you keep it in the outlet, you're going to have if you put it in the outlet and take it right out, that light is not going to be on because you only had one jolt of electricity, one action potential. It's not going to do anything. But what you have to do is keep that plug in, and you got to have an action potential after an action potential after an action potential. You're going to have a frequency of action potentials. That's going to do work. So we need to make sure that we have a ton of action potentials right after each one. Okay. So far, does anybody have any questions before I go further? Because this is a big concept.
So the action potential actually happens when it goes into hyperpolarization?
After hyperpolarization, it's going to go back to its resting potential here. So the action, I'm sorry, go back to its membrane potential, resting membrane potential here.
So when it returns, so it starts off at its resting membrane potential, and then when it returns to it,
Yes,
is the action potential.
right. And then it's ready to do another action potential.
Okay.
So you would have another one and another one and another one. If the stimulus is still there, if there's pressure or light to allow you to see, if the stimulus is still there, then there's going to be more sodium going to be going into the cell. And if it reaches negative 55, you'll have an action potential.
Okay, so the stimulus starts at 70. Boop, boop. That's one action potential.
Right.
Goes back to 70, and then it happens again.
If the stimulus is still there, yes.
Yeah.
Okay.
So the whole process of the action potential is the depolarization, repolarization, hyperpolarization, resting
Right.
membrane potential. Okay.
Exactly. And with that said, another key thing about this is that if it reaches negative 55, you have enough stimulus, enough pressure, enough light to actually get it to negative 55. This is important right here. If it reaches negative 55, you'll have a full action potential. There's no such thing as a partial action potential. All right. You either have an action potential or you don't have an action potential. It's the all, we refer to it as the all or none principle.
Okay.
If it goes to only negative 60, then you didn't start an action potential. It'll never reach negative 55. You won't have this whole thing happening. It has to reach negative 55, and you will have a full action potential. That doesn't go like halfway. It will go all the way. It's either you have one or you don't.
Okay.
Okay. Now, the other thing too, if I stimulate the cell, stimulate the cell when an action potential is happening at this level here, you are not going to get another action potential going up like this. That does not happen. It has to go right back down to negative 70 again over here. Remember, it passes right through here, so you're not going to get an action potential if it passes here. It has to reach negative 70 again for you to have another action potential. You will never get another action potential if you stimulate it here. It's either you have all of it or none of it. It has to reach negative 55. And that's a key concept. Questions about that?
So it basically has to go through this entire process before you get another action potential.
Correct. Now, when you say the entire process, yes, we're talking about a split second. But yes, you're absolutely right. You won't be able to do any work if you don't have this action potential happening. So I want to get people's questions before I go on to the next concept about the action potential. Anyone, just unmute yourself and just ask.
I kind of just had another question that goes
Go
on.
ahead.
So there's like no way that it could skip like hyperpolarization and start another action potential. It just has to do like
Yes, yes. So in other words, it can skip it, but that's what I want to talk about next. But before we get into that, anybody have any questions about this concept here? That's good, Lynette. We're going to lead right into that. No? Okay, so let's talk about, remember how I said over here, let me get the, so you have this neuron, right? And you have the very fast. So we talked about an action potential going down this axon, and it has to be one after the other. Okay, but remember, we have an action potential that's going to happen over here too. And that's why I'm talking about an action potential in our muscle system, because we have this action potential that's happening here. But they kind of do the same thing, whether you learn it from here or over here. It's still the sodium potassium. But look at what I'm doing here. See how I'm putting arrows? They're all going this way. How does it know not to go backwards? That's what I got to talk about here. And it goes into what Lynette was asking. Okay, so there are what we refer to as refractory periods, where when this action potential is happening, you can't start another action potential until this reaches -70 again. The best way I could explain this, again, my analogies, salty bananas and are off the wall, but it seems to work. Well, my analogy for this, for you to understand that it doesn't go, you can't start another action potential when one is already going. Think of the action potential as your toilet bowl. Not the toilet bowl that's in school, but your toilet bowl that people have in their house. Now, when you flush the toilet, whoosh, and it goes down, you can't flush it again until the tank fills with water. You could, I don't care how hard you're going to press down on that handle, you're not going to be able to flush it with until that tank fills again. So think of that same concept here, is that you can't have another action potential until that action potential fully gets back to -70. So we have two types of refractory periods. There's something called an absolute refractory period, where there is absolutely no way that an action potential can happen again during this thing. And it happens from this point here to this point here. You cannot, like I said, if you stimulate the nerve happening right here, you're not going to have another action potential. It has to reach down here. It's absolutely a refractory period. Okay? Then there's something called a relative refractory period, where it can happen anywhere during hyperpolarization. If the stimulus is, let's say we want to stimulate the cell at this point, which is maybe -80, you can start another action potential from here to go up and do all that, as long as that stimulus is very, very strong. You see, before we had to go from -70 to -55. That's only 15 points. But now, if you have to go from -80 to -55, that's 25 points. So you got to have a really strong stimulus to really do that. Otherwise, you have to wait until -70, which will go there eventually. So an absolute refractory period is absolutely no action potential could happen between this block right here, but you could have a refractory period where it can be anywhere from here to here during hyperpolarization. But the stimulus has to be extremely strong. Does that answer your question, Lynette?
Yeah, it does. Thank you.
Okay.
When you say extremely strong, what kind of stimulus are you talking about?
It could be any kind of stimulus, whatever that cell is usually gaining that stimulus from, whether it's a light and then the stimulus actually does something for your eye, or there could be pain, whatever that is. We'll go into different stimuli when we get to nervous system. It could be pressure, it could be anything.
Okay.
Okay. Whatever it can do to get from, let's say, -85 to -55, 30 points, when it usually would only take 15 points, but it has to be really strong. Other questions so far?
I just had another question about, because I know you said you can't have like half an action potential.
Correct.
If that, like, let's say that was a thing, what might that look like?
I have no idea because it doesn't exist.
Okay.
Yeah. I guess what I was trying to show you is that a partial one would be like, it would only go to, let's say, here and go down. Or if you stimulate it at this point, if there was no absolute refractory period, then you would have another one going up like this and going down. But we don't see that. It has to go up and down to do that. And because of that, it only goes one way. Because if this one goes, it can't go backwards because we just had an action potential. This one's still in a refractory period. So it can't go backwards. Does that make sense?
Yeah,
That's where that comes in.
Dr. Kamara,
Yes.
I think a good way to kind of conceptualize why a half one wouldn't exist is that when that cell receives a stimuli and completely depolarizes, that's when it affects whatever action it's designed to do, right? So like a muscle cell would then contract. And so if it didn't completely repolarize and you had a half action potential, it wouldn't contract the muscle. So that's why it doesn't do that, right?
Right, but you got to keep in mind, but you got to keep in mind too that one action potential is not going to contract the muscle at all.
Okay.
You know what I'm saying? You got to have one after the other, after the other, after the other. It's got to have a brigade.
Got it. Okay.
Yeah, you got to one action potential. It's just not going to do it. You know, a cotton ball that touches your shoulder is not going to move you out of the way. But some guy that's going to shove you is going to move you out of the way. But a cotton ball is really not going to do anything. So it has to be one after the other. Like maybe the guy is shoving him, but he's pushing him. Maybe one push isn't going to move you, but a brigade of pushes will say, okay, I'm in his way. I got to move out of his way.
Right.
Does that make sense to everybody? So there's certain rules, but they're explained because of these absolute and relative refractory periods, like a toilet bowl. And that's why it doesn't go backwards.
And the refractory period is from -55 back down to 70 at repolarization, right?
Which refractory period? Absolute or relative?
Oh, absolute.
Absolute, yes. It's basically during this time here, all through this is absolute.
And then that little chunk.
And this little area here is refractory, or I'm sorry, is relative. Because it's relative. It depends on if it's a very strong one. a strong stimulus. Whereas the absolute, it's absolutely, there's no way you're going to start that. Like a toilet bowl, you know, as soon as you flush it, you want to hit that handlebar. I don't care how hard you hit that handlebar, it's not going to flush again because the tank has to fill up with water again. But then it comes to the point where at the very end of, let's say, if it didn't quite fill up the gas, the water tank, but it's almost there, maybe an inch away. And if you hit that handlebar really hard, it'll flush and make the water go down. Took me a long time to come up with that analogy, but
Yeah, it's a good one.
yeah,
So that can happen during the hyperpolarization.
correct. Yep, right.
And what did you call it again? Not absolute. You called it the what? The
Relative.
relative. Okay.
Okay. I know there's a lot here, but it's once you get it, it's like an epiphany. It's like, wow, why did I have a hard time in the first place? And like, this is kind of neat how this all happens. Because then when I get into the intro to nervous system, I'm gonna show you how to apply that. Like what happens if we have too much potassium on the outside here? Then this is not gonna, we talk about simple diffusion, then this is not gonna happen so fast. And it's gonna stay more positive in here. And if it stays more positive in here and it doesn't reach negative 55, it's like right around here, you're not gonna have another action potential. We have a medication. Someone talked about lidocaine. So let's talk about this one. Okay. So we have a medication called lidocaine. So let me just explain to you what that does. Lidocaine opens chloride channels. So look what's going to happen here. Let me use, so I'm going to use chloride as green. So just jumping ahead, because I'll be doing this in intro to nervous system. But we have more potassium over here. I'm sorry, chloride. Sorry, chloride. And we have a couple in here. So which way, if these chloride channels open, it has nothing to do with the action potential, right? We didn't talk about anything with green over here. But look what happens. If we have chloride channels here and we have a medication that would open this, does chloride want to go into the cell or out of the cell?
Into.
To the cell.
There, you're all getting it. Good. Goes into the cell. If it goes into the cell, does that make the cell more negative or more positive?
Negative.
More negative.
More negative. So look what happens to the membrane potential. The membrane potential, if you're saying that the membrane potential is going to be more negative now it's going to be, let's say, it could be negative 90. So we now, for us to have another action potential, we needed to go from negative 90 all the way to negative 55. You need a really strong stimulus to get that action potential going. So if you open chloride channels, we tend to have an action potential or not?
Not.
Not. It actually hyperpolarizes. It goes down even further. Now, how does that come into play with my way of applying things? Okay. You put a needle in your hand. An action potential is going to go from your hand, through your arm, up your spinal cord, to your brain, and your brain is then going to interpret that's pain and is going to then send another action potential to certain certain muscles in your body to move away from there because the pain is too painful. But if I put lidocaine and let's say it's a cream and I put it all over the palm of my hand, and then I put a needle in my palm of my hand, Lidocaine is going to open chloride channels. Will I be able to have an action potential go to my brain? Anyone?
No.
No. So am I going to interpret that there's pain there?
No.
No.
No. That's what happens. In certain medications, we could, if we hyperpolarize, let's say for pain medications, not all pain medications, there's others, there's other things going, they have other mechanisms, but I'm just giving you an example of one. But if you have something that's going to open chloride channels, then that can be utilized as no action potential, no pain. We can also have a medication that is going to close sodium channels. If you close sodium channels, will you have an action potential? Will you not have an action potential?
No, because it won't depolarize.
Won't depolarize, yeah. So again, you won't have an action potential. So when you get into pharmacology later on in your career, if that's going to be a course of yours, which I'm sure many of you it is, you need to go back to the action potential because they're going to ask you about mechanisms of certain medications. And instead of memorizing, oh, it opens chloride channels, oh, it closes sodium. I mean, you still got to understand it, but you need to understand the action potential for you to appreciate what the mechanism is. And that's going to, instead of just doing rote memorization of, oh, it decreases the depolarization and not knowing what depolarization is, when I'm teaching it here, you're going to need to know it later on. So you might as well just make sure you understand the concept now so that later on, all you have to do is review it, not relearn it. But it's a really interesting thing. And then you could see how all the applications can happen here. Do we have any questions before I do the last thing with you guys? No? Okay. So sorry.
I have one question, but I might be getting ahead of myself. So if I am, just change it. But so you mentioned that at -70, the resting membrane potential, that's like when we're sleeping, right?
Well,
So
I mean, I don't want you to think that nothing's happening because there are things happening. You're breathing. So your diaphragm is still, but I'm talking about your skeletal muscles, unless you're moving.
Yeah, so that was my question. That's primarily for the voluntary muscles.
No, because it's also happening with your diaphragm. You're not even thinking about breathing. And you're not thinking about smooth muscle that's all around your intestines. So you're not even, or your heart beating, which is cardiac muscle. So things are still happening. But it's just not, your involuntary muscles are also doing that too. Or let's say you're lying on your side and you're sleeping, but now you got pressure going on, let's say your shoulder. Now you're still sleeping, but you're feeling like some kind of uncomfortability there. So then you move your whole body. So you got pain or pressure that goes, an action potential goes from your shoulder up to your brain. Your brain says, oh, this is not a comfortable thing. So it sends another action potential going down to your muscles so that you move away.
Yeah, that's what I was trying to get at.
Yeah.
This is constantly happening all the time, at all moments. Yeah.
On all your cells. Yep.
Everything. Yeah.
Right. Even your liver cell. Now that's not a neuron and that's not a muscle cell, but they have its own membrane potential to make sure it can, all the different things that the liver does. So every cell in your body has action potentials. It's just not everyone has -70. It might have something else.
Right.
But the muscle and nerve definitely have -70.
Okay.
Yeah. I'm fascinated. I mean, I don't know. I'm fascinated by it. Once you get it and then how to apply it, it's like amazing how this all happens.
Yeah, I find it fascinating too.
Yeah.
I mean,
But we're showing you how you're building, how like biology 121. If you don't know what simple diffusion is, if you don't know what an ion is, it's not gonna, you got to review all that. But once you do, we're building on this. Any questions with what I've been talking about so far?
So if you have like nerve damage or anything like that, do these action potentials, does this whole process just not happen, or like what occurs with that?
Yeah, so if we start doing nerve damage, so you crush a nerve. Is that a good example?
I think
I mean,
so.
yeah, it could be crush a nerve, you cut a nerve. Yeah, if I crush if my arm gets crushed, okay, I don't know, doing whatever, it gets crushed, it gets to the point where you're cutting the nerves from your hand to your brain. So you do feel pain because right where, let's say, the crush is, that's where the pain is, but you're not going to feel anything at your hand. It's going to be numb at your hand, but you're going to feel pain, let's say, in the middle of your forearm, because you block the action potential coming from your hand. Even if you put a needle in your hand, you're not going to feel it because we damaged the nerve coming from the hand. Now, there's another thing that I don't want to get into, but the phantom limb, where even if your hand gets cut off, it feels as though you still have a hand and you could still like move them. That's because some of the nerves are still there, but the ends of the nerves are not. So it's going to a severed part. So even though because you haven't done anything with your brain, so your brain thinks you still have fingers. So it still has a connection to, let's say, the muscles of your fingers that you once had. So it's going to send it, but then it goes to the stump of your arm and it just doesn't go anywhere. So your brain still thinks there's a phantom limb there, a phantom hand. So I like your question. It could be complicated, but yes, it could be crushed and damaged in that way. Or remember how we talked about multiple sclerosis, that we have that myelin that protects it. But if that myelin starts coming off or degenerating, getting destroyed, now you're not going to be able to, that action potential is going to fire like outside of the axon itself, and it never gets to your brain, or it never goes to your muscle if it's going the opposite way. So then you're not going to be able to move that muscle. So there's a lot of things that can damage, and I like your question because it's applying things, but there's so many different things that could happen, and it kind of opens up a lot of different things. But like I just explained to you, phantom limb, you get your arm crushed, you know, there's so many different things. But the concept that it stops an action potential, it never reaches your brain, you won't feel the pain. Or you're going the opposite way, it wants to move those fingers, but the fingers are, you know, there's some kind of blockade that happened at the arm. So you're not going to move those fingers.
Okay, that makes sense. Thank you.
All right. I know I'm using the hands and the muscles, but like Margaret, I was explaining to Margaret, remember, it's also things, just think of other muscles too. Like the smooth muscle around your intestines, you know, that can also get damaged. Or the smooth, or the cardiac muscle. You can imagine all the different things that can happen there. But it's also like what I showed up here. This is a neuromuscular junction where a nerve goes to a muscle. But we could also have a nerve going to another nerve, to another nerve, to another nerve. And that's, a lot of that happens inside of our brain. It goes to one part of our brain, but how does it go to another part of the brain? By that neuron attaching to another neuron, to another neuron. And how it talks or communicates from one neuron to another is action potentials. So there's a lot of neural medications that could affect the brain in stopping or stimulating action potentials in the brain. someone having a lot of seizures. There's firing action potentials when they shouldn't be firing. That's what the whole concept is with epilepsy. So sometimes, if it gets so severe, that he can't breathe, like it attacks the digestive or the diaphragm, they can go in and they could burn certain parts of the brain that is firing too much. Why it does that, it's probably has something to do with these ions, that it's allowing too much sodium coming in or too much potassium going out. And they start off with Tegretol and certain medications that would control these kinds of things to slow them down. And that's why they have these tonic-clonic seizures that you typically see like in that way. Or it could just be petite seizures, which is like they're just staring into space. But again, I'm going off topic, but I'm just emphasizing, I've been using muscles, the neuromuscular junction, but keep in mind, action potentials also go from neuron to neuron also.
I can be way off. Is that what carpal tunnel is?
No, carpal tunnel syndrome, well, in a way, a carpal tunnel syndrome is the median nerve in your wrist and pressure going on it. So it's also talking a little bit about what Lynette was talking about is I wouldn't say it's damaging, but it's putting a lot of pressure on that nerve. And that's gonna open up more action potentials. The pressure is, you have too much pressure, it's gonna cause pain. So that pressure that's happening there is gonna go back to your brain and the brain's gonna sense, it's gonna be pain to you.
Yeah, I had it for about 2 months. It cleared on its own, thank God, but it was unbelievable.
Yeah, and did you have a brace?
Yeah, I ended up using a brace and switching the way I slept and different.
Right.
I did all kinds of home remedies before I went to the doctor, and thank God it went away. But it was crazy.
Yeah,
it was just like a frayed wire.
Yeah, the brace, what that does is it makes your wrist not move in a certain way, so it helps relieve. Usually it's an inflamed area, or there could be a lot of water that gets in there. We call it edema. We see it a lot in pregnancy also. In pregnancy, because they get a lot more water, a lot more swellings in their legs and their arms and stuff. So that extra water in the wrist is pressing down on the median nerve. So we usually see that. It's not infrequent that we see it. We see it. But that's the reason why. So we usually give them a brace and, tell them like, if you could live with it, we wouldn't want to do surgery with that because it's only going to be a temporary thing until, she delivers the baby. But anything that's pressing on that median nerve is going to be the carpal tunnel syndrome. Yeah, good. Okay. Other questions? These are all great questions. Tell me everybody is active. Yeah. Okay, so let me erase something here because I just have to, and this will only take like about 5 or 10 minutes to do. Last thing I want to just talk about is the concept of what happens. I mean, there should be a question that everybody should be thinking about. Okay, the question I'm saying is, okay, if sodium's coming in and potassium's going out, eventually the potassium is going to go out here and it's going to equalize, right? It's going to be, if there'll be, let's say, I'm just talking about the blue here, but there'll be, let's say, 25 dots here and 25 dots here. Right? If it's all going to go out because of simple diffusion happens until it becomes isotonic. Same way with here. Right? I just want to erase this. Just want to talk about these two. Okay? So we have a problem here, a big problem, that eventually there's going to be 25 sodium here and 25 in here. Potassium will be 25 here and then 25 here. If that is 25 and 25 and 25 and 25, the resting membrane potential is going to be 0, which means you're dead. You can't do anything with that. So we have to have a process that it has to be, let's just talk about sodium here. We have to have some kind of mechanism to make sure that we have more sodium on the outside than we have on the inside. Because I only talked about sodium coming in, but I never talked about sodium going back out where it belongs. But it won't do that because you're going to have a little bit of sodium here and a lot over here. We're going to go, you see, simple diffusion goes from a high concentration to a low concentration. A high concentration to a low concentration. It happens naturally. But what's the transport mechanism that we may be able to do to go from a low concentration to a high concentration? That is not natural. What is that? What is that transport mechanism?
Is it facilitated diffusion?
No, that's not facilitated. That's different. It's like putting a key in here and then opening it. You need some kind of thing to facilitate these channels to open up. These will just open up naturally.
Active transport?
Active transport. Active transport is what I want you to know. So you have active transport. Active transport is when we're going from a low concentration to a high concentration. That is not natural. If you have 3 people, in the classroom and you have 100 people in the hallway, if that door opens, it is not natural to have the 3 people from inside the cell going outside the cell. We can do that if we have some kind of special energy. What is that special energy that we can actually do that? What's that energy called? The
ADP.
ATP. ATP is the currency that we use for energy in our body. Now, using ATP we're going to need that to do work. We're going to go from a low concentration to a high concentration. And we have something called the sodium potassium pump. It's also referred to as the ATPase pump, because ATP is used for this. And what this is, let's see if I can draw this. Let's close here. What this is that we have trying to use the same colors here. And so this is our cell membrane. This is going to be the extracellular fluid. This will be the intracellular fluid. Intracellular fluid. Okay, so we have more potassium outside than inside. We also have more potassium inside than we have outside. But we have a special pump. So normally what we have is that potassium wants to go out of the cell and sodium wants to go into the cell. We have a special pump here. Let's see, we'll do in brown. And this here is called the sodium-potassium pump. Okay? What this does, ATP is needed for this. And what this does is that it's going to put 3 potassium in here. And it's going to take 3 potassium from out of here, and it's going to move it in this way. And it's going to take 2 sodium from inside, and it's going to move it back out that way. Now, why? Let me ask you this. Why is it that we have 3 potassium and not 3 sodium? Or why not 1 sodium and 1 potassium? Why do we have this odd number of 3 here versus 2? Who could answer that?
Because we need more potassium inside the cell?
No. Okay, let me ask you this. If I have 2 sodiums going out and 2 potassiums going in, what does that do to the charge?
It makes it more
Oh, it
negative.
make it-
No. Listen. 2 sodiums going out, and if I had 2 potassiums going in,
It would keep it equal.
it would keep it equal.
Okay.
Does that make sense?
Yeah.
Okay.
Is it more potassium because the potassium leaks greater?
It's more potassium. Yeah, that's part of it.
More
But
positive.
we need to make sure that it's going to have a different charge in here.
Yeah.
Okay. And yes, potassium is going to leak out more, but we don't want to have the same amount going in as we do out because they both have the same charge. This is going to reset. And when we had the action potential, this ATPase pump happens after each action potential to put it back. Otherwise, it'll, like I said, you'll have 25 potassium here and 25 in here. And then you're not going to have an action potential. It'll be just 0. The word potential in this way is that it has the potential of getting to 0. But if it's already 0, there is no potential. It's at 0. So we need to get that back. We need to make sure that the potassium goes back to where it belongs and the sodium goes back. But it's going from a low concentration to a high concentration, not a natural thing. So we got to use ATP to do that. And that'll be done by way of active transport. Now, to help you memorize the 3-2-2 over here, and this is the last thing I'll talk about, it's just a mnemonic here. You ever hear that song, na 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 na, na 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 na, hey, 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 goodbye, right? They played a lot of these sports events and things, right? You know that song? Now I got a cold, I'm singing, it's pretty pathetic. But so just think of, I'm sorry, you know, I just did this wrong. Because I just remember this. Sorry, I did this wrong. It's, shoot. Okay, I'm sorry. This is wrong. I'm so sorry, but a good thing I did this mnemonic. Today I haven't done it. What it is that it's the opposite I was saying. Everything I said was correct, except what ones go out, like how many. So what's happening, I'm sorry. So it's going to be 3 sodium going out. I'm sorry. And there's 2 potassium coming in. I'm sorry. Okay. And again, that's what that's going to do. And I should have known this, but what that's going to do is there's going to be more potassium, more sodium on the outside, making more positive out here. And then only 2 potassiums. That means it's going to be more negative inside when you compare that. You see, does that make sense? Because we're putting more positive outside and we're making less positive insight, but we're still putting the potassium back where it belongs. I'm sorry to confuse you. That's what's happening over here. But everything else I explained is correct. And what Lynette was saying, yes, that's part of the contribution of the potassium leaking so much. So now going back, and now it'll make sense that mnemonic, na 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 na, hey, hey. So I would say na na na. And how many times did I say na? 3. 1, 2, 3. So I just say na 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 out, na 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 out. KK goes inside. You're all mute, but I know you're all laughing like, oh my God, you know, what's my husband gonna think? What's he doing? I'm taking history here. Yeah. But yeah, does that mnemonic help you? All right.
Yeah.
So, you know, 3 sodium out, 2 potassium in. But understand why it's not 3 potassium out and 3 sodium out and 3 potassium in, because then it'll be equal. That defeats the purpose. The charge would be 0. But we still need to keep the charge so it's not 0, and we got to be sure that we can get the sodium back where it belongs and the potassium back where it belongs. I'm sorry to confuse you on that.
Okay.
All right. Do you have questions about that? I know I went a little bit over. Let me get back to this. What questions do you have? It's a big concept. It is. And like I said, I'll have this video if you want to watch it. You know, since everybody was here, you know what part you want to jump to. But everything I explained is in my video lecture. I do my drawings, salty banana, it's all up there. But I did want to do this with you, the hard concept. And I think that's what will do for the remaining times that we meet in person. I'll do the hard concepts that I think from what students have told me in the previous semesters. So the easier stuff you could watch me, but I want to get that real life questions and answers if you're lost on that now. No questions? All right. So that's all I wanted to talk about today. It's all good. Sorry with all the dates that we have holidays and stuff, but it seems to work out. And if you're really stumped on things, we could maybe do these. I would make it optional, but we could always do this kind of review thing. You know, I could do that if you're really stumped on bigger concepts throughout the weeks. You know, something like that. I have no problem. We'll make it hybrid now that you know how to work Zoom and all that. Good then? All right. My suggestion is grab something to eat or something like that. But my suggestion is just, if you took notes, is just go back. It's fresh in your mind. Go and just spend like 15, 20 minutes. Just make sure that any abbreviations you made, it's fresh in your mind. You just make sure those abbreviations make sense, or those fast scribbles make sense when you come back to it, let's say a day later. It's fresh in your mind now. That's what I always tell students after they go to class. Just spend some time doing that. All right. Any other questions, concerns? All right. Does anybody want to talk to me privately right after I send everyone back? No? All right. Well, enjoy the rest of your day. I'll see you all on Monday, 8:30. We'll do the lecture exam first. I'll try and do some, I want to try and do some things with like the bones. You know, if you're really, you don't need to bring in the bones. We have the bones over there. You know, if you want to use bones, there's no reason to, unless you want to bring the bones because you want to study in the cafeteria after class and you have the bones, but you can leave them in your car or whatever. But we have bones already in there. You don't need to bring them. And we'll go with that. Okay. And we have the same bones. So so Margaret, if there's some issue, we'll work that out. That's not enough. We'll work that out. Okay. Sound good? All right. So we'll all see you on Monday. Email me if you have any questions at all. I'm here for you.
Thank you.
All right.
Thank you.
Stay well.
Thank you.
All right. Bye-bye now.